Okay, so in section 1.1, we were looking specifically at categorical variables and learning how to graph and analyze and compare them. Section 1.2, we are switching over to look now at quantitative variables, so number variables. And we're going to take a look at what you do there. The types of graphs and the strategies we use are different for quantitative than they are for categorical. So let's get to it. We are starting out by looking at these two individuals who are looking to move to a new city, and they've got 7 cities to choose from here, and they want to look at the temperature in these cities over the course of the summer. So in June, July, and August, these are the daily high temperatures in each of these different cities. So this is everything in city A, etc. If you look at the bottom of the slide there, you can see the actual temperature that goes with it. So they're all graphed on the same scale. And what I'm going to have you do is look at these graphs here, graphs of quantitative data. Quantitative because they're numbers. We have the daily temperature for each day. And then notice that, first of all, the type of graph they choose to use here is a dot plot. Dot plots are great for quantitative variables. There are other types of graphs we will learn about in the next set of slides. But for now, we're just using one of these. But we want to talk about how you would describe or analyze a quantitative graph like this. So there are a few questions right here on this slide that I want you guys to consider. So first off, ABC, what's the biggest difference? Then C and D, then DE, then CFG. Go ahead and take a minute to look at this and try to explain what the difference is between these various pairs of cities here. For the most part, I'm looking for like a one-word answer for each of these things. And this will be like kind of an important topic that we talk about and formalize in the next couple slides. So take a minute or two to explore that yourself. Look at A, B, C, then C, D, etc. All right, so I'm going to go ahead and talk through this here. A, B, and C was the first one. And if you look at A, B, and C, there's those 3 distributions, and really they look the same. They're almost the same graph. They've just been shifted from side to side. So the position would be one way of talking about that. The average high temperature is going to be different. Like this city is warmer in general than this city. A simple one-word way of talking about how it just shifts from side to side like that, I'm going to say the center of those cities. The center is here versus here versus here. In a single word, the biggest difference between A, B, and C is going to be where their center is located. Then I asked you to look at D and E. So D and E are here versus here. D and E have about the same range to them. This city right here is pretty spread out, but it goes from the same low as city E and the same high as city E. But if you look, D is really, really spread out. E is really kind of compacted with those points on the ends. The biggest difference I would say between these is I guess there are kind of 2. Did I ask for 2 for this one? No, I did not. C, oh shoot, I'm looking at D and E. That's why I'm getting confused right here. If you look at C versus D, C goes from this range right here. That's a pretty close range to D being a lot more spread out. Temperatures in D go lower and higher than they do in C. C has a higher minimum and a lower maximum. In a word, D is more spread out than C is. C is a little more compact. So what's the biggest difference between C and D? C and D is spread. How spread out they're going to be. 2 differences between D and E, which explains why I was a little confused a second ago. There are 2 things going on between D and E. One would be that E has a lot of really popular values right here around 80 degrees, and then it gets less popular to either side. D is about equally popular of getting a 60-degree day and getting an almost 100-degree day. It's a pretty big grab bag of what's going to happen. E is a little more consistent. So the way that I could describe that right there is by talking about the shape of the distribution. So shape and spread are the 2 things that I'm talking about with regards to this one here. The shape, there's spread, And I'm actually going to throw in, I'm going to break my own rule right here. There are actually 3 things I want to mention. There also appear to be a few really weird outlier days in graph E. So if you look at graph E for just a second again, graph E has this day right here and this day right here that are definite outliers in the overall pattern. So while the minimum and maximum is the same in both, this one is a lot more packed together. So there is a difference in spread between these graphs, even though their maxes and mins are the same. There's a difference in the shape of the graphs. This one is a lot more peaked than this one right here. And this graph E has a couple outliers that the others don't. All right. So CFG is my last one here. So let me just circle those. I'm looking at C and F and G. So C is relatively symmetric. It's basically a mirror image on both sides. Sort of looks like a regular hill. F and G are what's called skewed, which we're going to define in a minute. This goes this way. This goes this way. So low temps are popular here, less common to have high temps. High temps popular here, less common to have low temps. Those 3 pictures are all very different in their shape. So I kind of spoiled that by mentioning shape in the last one. But shape is the single biggest difference there. So hopefully in talking through that, you might not have used those exact words, but you guys can appreciate the differences that exist between those different graphs. And it's very important when you describe a graph of quantitative data that you address those 4 concepts that I was kind of getting at in that last slide. So whenever you address a graph of quantitative data, the 4 things you need to make sure you address are shape, outliers, center, and spread. So those 4 features, anytime it says describe this quantitative graph for me, describe this graph, you need to address these 4 things. Now, how can you keep those 4 things straight? Well, they make a sweet little mnemonic right here, SOCS. Don't leave your socks at home. You got to remember your socks. Well, you got to remember your socks when you're talking about graph types here. So a SOCS question is very common. It's frequently on the AP test. And it's basically just making sure you talk about these 4 features of the graph. So it's not too bad to do either. Okay. So in order to be able to talk about SOCS, we need to develop a little bit of vocab right here. And there is a sweet picture that I am covering up with my face right here. So let me move myself over to this corner. This picture is from our book right here, and it's looking at skewed graphs. When you look at a graph being skewed, the direction of the skew is the direction that it tails out. Like if you were going to ski like that guy right there, the direction you would go down is the direction of the skew. So the bulk of the points on this graph right here are on the right side, and it slopes down to the left. This would be a skewed to the left graph. So the direction of the tail is the direction of the skew. So this graph right here appears to have a slight skew to the left. It goes downwards this way. This next graph here certainly isn't perfect, but I don't see a compelling argument for sliding down either side of it. If there was an extra few dots right here, it would be even easier to see. But this one is sort of symmetric. What you can say, since it's not perfectly symmetric, is you can say it's roughly symmetric. If it's more or less the same on both sides and you don't see strong evidence of skew, you could say roughly symmetric. And it says to draw a graph of the one we did not use. We did not talk about skewed to the right. Skewed to the right would have the bulk of the points on the left side, and then it would become less common towards the right side. So you're going to slope down that way. So that is how you talk about skew in a picture. There's other words that we also use to address shape. So all of the things that I just talked about right there were examples of vocab for shape. So are these words right here. These words, unimodal, bimodal, and uniform. Unimodal means one peak to the graph. Bimodal means 2 peaks to the graph. And when you talk about having a peak, a mode is the most common number, so it'd be like the maximum. They don't have to be exactly the same size. You're basically looking for how many bumps a picture had. If you look at this first picture over here, if I were to take like a blanket and like throw it over this graph right here, I would see 2 distinct bumps in that graph. So this is a bimodal picture, even though the right side has a slightly higher frequency than the left. So it's bimodal because there are two pretty distinct peaks. Now you could ask, like, it's sort of a judgment call. Like if they get closer and closer, at what points are they close enough that there's just one big peak, one bump under the blanket instead of two separate ones? And that's just a little bit of a judgment call. So use your best guess. We could maybe have one, like this one's pretty clearly bimodal, but let's say the second part of the picture was like this. Like how close do they have to be together before you call that unimodal instead? Like that's probably unimodal right there, but there can be a little bit of gray area. This picture over here is totally skewed to the left. That is a way of talking about the shape of the graph, but it's also unimodal. If you throw a blanket over this guy, there's the one big bump over here. So that's unimodal. And this last word, uniform, means more or less flat. Perfectly uniform means everything is equally popular, but it could be where this is like one more and it's like roughly uniform. So about the same as uniform, and then you have unimodal, bimodal, also words for addressing shape. All right. So when you talk about the shape of a graph, you'll be asked to give at least one word. So like if you're, I don't know if that's unimodal or bimodal, you could always talk about skew instead. So any of the words I've talked about so far are good ways of addressing shape. When you're asked to talk about a distribution in general, the two most important things that I see kids do wrong when they're asked to compare distributions. One is remembering context. That will be a big thing all class long. Talking about the actual context of the graph, not just saying the graph is skewed to the left, but like the graph of temperatures in these cities over the summer is skewed to the left. The other thing is remembering to explicitly compare the graphs. So making an explicit comparison is also going to be really important. That'll be easier to understand when we do our example on these slides, but basically compare the graphs to one another. Don't just talk about them both separately in a vacuum. So we have one big problem to talk about this whole thing right here, and we're being asked to compare the energy costs between freezers with refrigerators, or with freezers up top or freezers down at the bottom. So these are the energy costs of our top drawer freezers, and these are the bottom right there. So let's go ahead, and I gave myself more space here so I don't run out of room. Same exact graph we just saw. We just need to compare these two distributions. Anytime you are asked to talk about the shape of quantitative distributions, you need to make sure you address SOCS. All four of those things need to be talked about if you want full credit. So the first thing is shape. So people will say things like the graph is skewed to the right, and that's it. But you need to have context in your answer. I'm going to get some good context just by talking about the shape. So the distribution of top drawer energy costs, top drawer freezer energy costs, appears to be, instead of saying is, I'm going to say appears to be, which is a little bit softer in my language. You don't want to take too strong of a stance. I would call this, this is a little bit rough right here. I could maybe make an argument if that dot wasn't here, it's almost uniform looking. There is maybe a very, very slight skew to the right, but if that dot wasn't there, I definitely wouldn't call it skewed to the right. I'm going to say that it appears to be roughly symmetric. This is a judgment call right here. If I had a few more dots like this, then I'm going to say probably skewed to the right. But because it's just that one dot right there, I'm going to say this is roughly symmetric. It's about the same on both sides minus that one dot right there. Okay? Then you look at the shape of the other one, and you're like, ooh, I don't know. That one is kind of weird. Is it skewed right? Is it skewed left? You could maybe make an argument for like either. Maybe that's symmetric too. So if you're getting to a situation like that where you're like, oh, I don't know about skew, what is it? Is it something weird? You could also just talk about the other words for our shape. And that appears to be that this one is unimodal. So I'm going to be a little safer here, not even address skew, because like, oh, is it skewed left or right? Personally, I would say it's maybe a little bit to the right for that one. But I'm going to say that bottom drawers appears unimodal, Now I could stop right here. In general, with AP problems, you don't want to give away too much information because if you say a bunch of things and one of them is wrong, it will hurt your answer. So it's better just to say something and go with it. I'm going to leave it at that. I could say and slightly skewed to the right, but you don't want to over speak on these problems because if you say something wrong, you could have 7 really awesome things and 1 wrong thing that you just tossed in there and it will hurt your answer. So don't say too much, just address the main things. So yeah, that's shape taken care of. Then I'm going to talk about outliers. It doesn't have to be in this order, but it's a good way to go about it. No apparent outliers. In top freezers, but bottom has at least 1 outlier at maybe like $142. Okay? So you talk about the presence of outliers if they exist. No apparent outliers is a good phrase to use if it doesn't appear like there are any. So that's shape, that's outliers. Next up is center. Now we'll talk eventually about mean, median, stuff like that. Right now we don't know those words, so I'm just going to eyeball the center of this graph. The center of the data is somewhere around there for this one, and maybe it's somewhere around here for this one. When you talk about center and about spread in a second, mention actual numbers for the problem. So the center costs for top is approximately, and I'm going to use the word approximately kind of liberally right there, maybe 55 or so, I don't know. But here's where the other thing that I mentioned earlier comes into play. You need to explicitly compare the 2 graphs. So if I just say, oh, the top is 55, the bottom is about 70, that wouldn't get me full credit because I didn't say that one is bigger or smaller than the other. I didn't compare them. Now, it seems common sense that 55 is smaller than 70, but you have to say it. So I'm going to say which is less than the bottom center of about 72. So explicitly compare them. I have one more thing to talk about, and that is spread, and I'm going to delete that so I have more room right here. For spread, you could talk about the minimum and the maximum, and you could talk about the range as well, max minus min. But when you talk about range, you actually have to subtract the maximum minus the minimum. So I'm going to say not range, but I'm going to say that values for top vary from about 47 to, that'd be like 65, which is less variable or less spread out than than the bottom, which varies from about 47 to 142. You can also talk about the not outliers. So if the outlier is like, you don't want to address that, you could say it goes from to 108, not counting outliers. So these problems are a tiny bit tedious to write out, and kids sometimes don't like them for that reason. They're really not bad, though, as long as you give enough detail. Shape, outliers, center, and spread are the 4 things you need to address when talking about quantitative graphs. And when you're comparing 2 graphs, make sure you actually compare them.